good evening, and welcome once more to the Sleepy Professor. I hope you found your way to somewhere truly comfortable this evening, perhaps lying back in a space where the world feels just a little softer, where the lights have been dimmed low, and where your mind is ready, so ready, to drift like a cloud at sunset, weightless and free. Tonight, on this quiet evening, wherever you find yourself in this vast turning world, we're embarking on a gentle voyage, a slow, peaceful journey into one of nature's most familiar and yet most deeply mysterious wonders, the secret life of clouds. Those quiet travelers above us, those ancient, timeless wanderers that paint the sky in endless, ever-shifting patterns, that shape the weather we feel on our skin, the rain that touches our faces, the warmth of sunlight filtering through their soft edges, and that, whether we truly realize it or not, whether we ever stop to think about it or not, help make life on this beautiful, fragile earth not just possible, but comfortable, livable, gentle. These floating islands of vapor above us are working every moment, every single second, to keep our world balanced, to keep temperatures steady, to distribute water across continents, to reflect light back into space and trap warmth near the surface. They are, in the truest sense, the invisible hands that cradle our planet. But there's so much more to their story than we often realize. Each cloud you've ever seen, each wisp, each towering giant, each thin veil stretched across the evening sky represents a moment in an ancient cycle that's been running since the first oceans formed billions of years ago. Water rising, air cooling, droplets forming, rain falling, and then the cycle beginning again, over and over, endlessly, tirelessly. Before we begin this slow, meandering journey together, before we drift upward into the realm of mist and droplets, I'd love to know, I'm so curious to know, where are you watching from tonight? Where in this wide world have you found yourself? Is it cloudy where you are right now, a soft grey ceiling stretching from horizon to horizon, or perhaps you're gazing out at a clear, starry night, watching the darkness settle slowly, gently, like a soft, warm blanket being pulled over the world. Maybe you can see the moon hanging bright and round above you, or maybe it's hidden behind a veil of thin cirrus, casting a gentle halo through the ice crystals. Perhaps you're in a place where clouds are gathering right now as you listen, where the afternoon heat is just beginning to trigger those first innocent puffs that might grow into something more dramatic by evening. Or maybe you're somewhere where clouds are breaking apart after a storm, revealing glimpses of blue between the grey, like curtains slowly opening to reveal a stage. It's always so fascinating, so wonderfully calming, so deeply peaceful to think about where in this vast turning, breathing world these gentle journeys reach. Someone might be watching this from a rainy city, droplets streaming down their window, the streets below glistening with reflected light. Another person might be tucked in bed in a place where snow is falling softly outside, each flake a tiny piece of cloud that has completed its journey to Earth. And still another might be listening in a warm room where the sun has just set and the first stars are beginning to appear, twinkling through gaps in the evening clouds. Wherever you are, whatever the sky looks like above you, you're here now. And that's what matters. You've chosen to spend this time learning, relaxing, and perhaps drifting gently towards sleep. If this video helps you relax, if it carries you softly, slowly toward sleep like a boat drifting on calm water, or if you simply enjoy exploring the quiet corners of science at a slower, more restful, more meditative pace, please consider giving it a like and subscribing to the Sleepy Professor. To those of you who have already joined this gentle corner of the internet, this peaceful sanctuary of knowledge and rest, this calm harbor away from the noise and rush of the world, thank you. Thank you so much. Your presence here, your choice to spend your precious time in this space, means more than you know, more than words can fully express. Each time you return, each time you choose to learn and rest with us, you're part of a growing community, of curious minds who believe that knowledge doesn't have to be loud or rushed, that learning can be gentle, that science can be a lullaby, that understanding the world around us can be both intellectually satisfying and deeply, profoundly relaxing. And if you haven't already, if this is your first time here, or if you've been thinking about it, you can tap that notification bell so you won't miss the next time we drift off together into another quiet story from the universe. Each video, every single one, is a soft invitation to let go, to learn something beautiful and true, and to sleep, to rest your mind while feeding your curiosity. Now, I do hope this video doesn't end up being so interesting that it keeps you awake. That's always the paradox, isn't it? We want to make these journeys engaging enough to hold your attention, to spark wonder, to make you see the world in a new way, but not so stimulating that sleep becomes impossible. But if it does keep you awake for a while, if you find yourself listening all the way through, at least you'll drift off eventually, knowing just a little more about how the sky breathes, how it moves in its ancient rhythms, how it lives and changes above us every single moment of every single day. And that knowledge, that gentle awareness of the world around you, can be its own kind of comfort, its own kind of peace. There's something deeply satisfying about understanding how things work, about knowing that the clouds above aren't just random. They follow patterns, they obey laws, they tell stories if you know how to read them. It's like learning a new language, the language of the sky, spoken in vapor and ice and light. So, take a moment now, and let me ask you something. What exactly is a cloud? Have you ever really stopped to think about it? Not just glancing at the sky, but really considering what you're seeing. And how does something that looks so soft, so weightless, so impossibly delicate and ethereal, manage to hold up millions upon millions of tons of water, suspended there impossibly in the air above us, floating as if by magic? How can something that appears lighter than cotton candy contain more water than 1,000 swimming pools? Think about it for just a moment. A single cumulus cloud, one of those puffy white clouds you see on a summer day, might weigh as much as 100 elephants. 100 elephants floating in the sky, and a large thunderstorm cloud, one of those towering giants that dominates the horizon, might contain the equivalent of millions of tons of water, more water than flows through most rivers in a day. All of it, every single drop, suspended in the air. A cloud, you see, when you really look at it, when you really understand what it is one of nature's most beautiful illusions, one of the atmosphere's most elegant magic tricks, an enormous structure, vast beyond our usual comprehension, stretching sometimes for hundreds of kilometers, yet made of the tiniest, most delicate things imaginable. Each cloud, every single one you've ever seen, is a congregation, a gathering, a community of countless microscopic droplets or ice crystals, billions and billions of them, trillions even, all floating together in the most delicate, precarious balance between gravity pulling down, always pulling down, and air pushing up, supporting them, holding them aloft. What we see from the ground as soft and fluffy, as something we might want to lie upon like a pillow in the sky, as something that looks solid enough to walk on, is really a complex, ever-shifting dance, a dance of temperature rising and falling, a dance of motion, air currents swirling and mixing, a dance of moisture condensing and evaporating, a dance that never stops, never pauses, never rests. To truly understand clouds, to really feel what they are in your bones, we have to start with something invisible, something you can't see, can't touch, can't directly perceive at all. We have to begin with water vapor, the unseen breath of the planet itself, the ghost of water floating all around us. Right now, as you listen to these words, there is water vapor in the air around you, invisible, odorless, silent, but present nonetheless. Every breath you take contains it. Every room you've ever been in holds it. It's been there your entire life, surrounding you, accompanying you, and yet you've never seen it directly. This invisible moisture comes from everywhere, from oceans releasing water into the air through evaporation, from lakes and rivers giving up their surfaces molecule by molecule, from soil and plants breathing out moisture through their roots and leaves, from your own body as you exhale warm, humid air with each breath, even from wet streets drying after rain, from morning dew evaporating as the sun rises, from snow slowly sublimating directly from solid to gas without ever becoming liquid. The air is constantly holding water, carrying it, transporting it from place to place. Sometimes just a little in dry deserts, where the air feels crisp and parched. Sometimes a lot in tropical rainforests where the air feels thick enough to drink, but always some amount, always some invisible cargo of moisture. Warm air, you see, you might have heard this before, can hold more vapor than cold air can, much more. It's like a sponge, and this is such a useful way to think about it. Warm air is an open, thirsty sponge, ready and willing to absorb moisture, while cold air is one that's already full, saturated, unable to hold any more. The warmer the air becomes, the more energetic its molecules, the more space there is between them, and the more water vapor can fit in those spaces. Cold air is the opposite, its molecules moving more slowly, packed more closely together, leaving less room for water vapor to hide. And as air rises upward, climbing slowly, steadily through the atmosphere, meter by meter, kilometer by kilometer, it cools gradually with each passing moment. The higher it goes, the cooler it becomes. This is one of the fundamental rules of our atmosphere. Height equals cold, always, invariably, predictably. Eventually, after rising perhaps a few hundred meters, or maybe several thousand, it reaches a moment of transformation, a threshold, a boundary between two states of being. We call this the dew point, the temperature at which air can no longer hold all its moisture as invisible vapor. Here, at this precise specific temperature, invisible vapor becomes visible droplets. The ghost becomes solid. The unseen becomes seen, forming the first faint, delicate threads of cloud. In that single instant, in that miraculous moment of transformation, the sky turns from transparent to tangible, from nothing we can see, from empty blue to something we can watch drift slowly by. Every wisp you see above you, every delicate curl and billow, every tower and sheet and streak, marks a place where the atmosphere has changed its mind, where heat has turned to coolness, where air has gently released what it was holding, letting go of its invisible cargo. Clouds are, in a very real way, in a poetic but also scientific way, the Earth's gentle exhalations, its quiet sighs, its visible breath. They're the atmosphere making itself known, making itself seen, revealing its hidden workings to anyone who looks up. They're so much more than decoration, you know, so much more than pretty scenery. They regulate the planet's temperature with remarkable, astounding precision. They reflect sunlight back into the cold, dark infinity of space. They trap heat below like the softest, warmest blanket you've ever felt. And they return water to the surface as rain or snow, completing the endless, eternal cycle that sustains all life on this planet. Without them, without these floating gardens of vapor, our world would swing wildly, violently between freezing nights that would crack stone and split trees and scorching days that would burn the land and boil the seas. The temperature swings on the moon, which has no atmosphere and no clouds, can be more than 250 degrees Celsius between day and night, from burning hot to frozen solid, utterly inhospitable to life as we know it. With them, with their patient, constant presence, the climate softens, the planet breathes evenly, steadily, regularly like you're breathing now, in and out, rise and fall, warm and cool, day and night, summer and winter, all moderated, all balanced, all made gentler by these floating islands of moisture. But despite their beauty and their profound essential importance, despite how much we've learned about them, clouds are still one of the great puzzles of modern science, one of nature's remaining mysteries. Satellites circle the Earth continuously, watching, photographing, measuring. Computers model their behavior with ever-increasing sophistication and power. Scientists have spent entire careers studying them, and yet, no single equation, no perfect, elegant formula can fully capture their complexity. They shift and shimmer. They change and evolve. They grow and shrink, never staying still long enough to be entirely understood. They surprise us. They defy our predictions. They remind us that nature will always be slightly beyond our complete understanding, that there will always be more to learn, more to discover, more mysteries waiting to be unraveled. In this quiet journey tonight, over the next hour or so, we'll drift through the many faces of clouds together, hand in hand, metaphorically speaking. We'll discover how they are born from the smallest seeds, from specks of dust smaller than you can imagine, how they live their brief, beautiful lives, growing and changing, and how they fade away like dreams at dawn, dissolving back into invisibility. We'll wander from the tiny salt grains blown from ocean waves that start their formation, to the thunderheads that tower over entire continents like mountains of vapor, like skyscrapers made of nothing but air and water, and to the wispy cirrus clouds that drift higher than any bird can fly, higher than most airplanes ever go. Along the way, as we drift from topic to topic, we'll see how these floating gardens of vapor shape the weather we experience each day, how they influence the climate of the entire planet over decades and centuries, and how they fill our skies with endless ever-changing stories written in white and grey. We'll explore the science, yes, but also the wonder, the facts, but also the feeling. Because clouds are both things at once. They're measurable, quantifiable phenomena that follow physical laws, and they're also beautiful, moving, inspiring presences that touch something deeper in us than mere knowledge can explain. So, take a deep breath now. Deeper still, feel your lungs expand fully, and let your thoughts slow down like a river, finding calmer water after rushing rapids. Let your shoulders drop away from your ears. Let tension melt away like morning mist in warm sunlight. Let your jaw unclench if it's tight. The world outside is still turning. Yes, the planet's still spinning beneath you. But at this moment, right now, that doesn't concern you. The clouds above are still moving in their ancient, timeless patterns, and together, you and I, we're about to discover something beautiful. We're about to learn how something so impossibly soft, so delicate it seems, it could vanish in a breath, can hold the power to change the entire earth below. Are you ready? Then let's begin. The birth of a cloud. High above the ground, miles and miles above where we stand, where the air begins to grow cool and thin and rarefied, where the atmosphere starts its gradual, imperceptible fade into the infinite darkness of space, a quiet transformation unfolds. It's a transformation so gentle, so subtle, so whisper-soft, that it usually goes completely unnoticed by those of us below, going about our daily lives. The story of every cloud, each and every single one that has ever drifted across the sky, begins not with thunder crashing or lightning splitting the darkness, not with drama or spectacle or fanfare, but with a single invisible breath of vapor deciding, simply, quietly, deciding that it has cooled enough to reveal itself to the world. This is the precise moment when the unseen becomes seen, when air, ordinary air, turns visible before our very eyes, when the sky paints its first soft, delicate brushstroke across the endless blue canvas stretching above. To truly understand this delicate threshold, this invisible boundary between states of being, imagine for a moment the air around you as a sponge, not just any sponge, but a living, breathing sponge with remarkable properties. Warm air, like a dry, freshly wrung sponge pulled straight from the sink, can hold a great deal of water vapor. An astonishing amount, really. Tiny invisible molecules, each one composed of two hydrogen atoms bonded to a single oxygen atom, bouncing freely, energetically, chaotically between the oxygen and nitrogen molecules that make up the vast majority of our atmosphere. These water molecules are in constant motion, vibrating, spinning, colliding with one another, thousands of times per second. They're moving so fast, bouncing around so frantically, that they remain completely separate from each other, individual molecules careening through space like tiny billiard balls in an endless game. They're invisible to us because they're dispersed, spread so far apart that light passes right through them without scattering. They're the ghosts of water, present but unseen, waiting for their moment to materialize. You could have millions of them in a single cubic centimeter of air, and you'd never know they were there. No hint, no clue, just clear, transparent air. But as the air cools, as it gradually, inevitably loses its precious warmth to the vast coldness of space above, that sponge begins to shrink. It can no longer hold the same generous amount of moisture it once did. The capacity diminishes with every degree the temperature drops. The molecules slow down, move less frantically, and suddenly there's not enough space, not enough room for all of them to remain as separate individual vapor molecules. And what it can't carry anymore, what it simply must release, condenses into droplets so incredibly small, so impossibly tiny, that you could fit thousands upon thousands of them on the head of a single pin, hundreds of thousands even, maybe millions depending on how generously you define a pinhead. That magical turning point, that precise, specific temperature where everything changes, is called the dew point. The temperature at which vapor begins its miraculous transformation, begins its journey from invisible gas to visible liquid water. This is where clouds are born, right here, in this invisible threshold between vapor and liquid, between the seen and unseen worlds. The dew point isn't some abstract concept that only meteorologists care about. It's actually something you experience every day in subtle ways. When you take a cold drink out of the refrigerator on a humid day and it immediately begins to sweat, droplets forming on the outside of the glass, that's the dew point at work. The cold glass has cooled the air immediately surrounding it below its dew point, and invisible vapor has suddenly become visible water. When your bathroom mirror fogs up after a hot shower, when frost forms on your car windows on a cold morning, when you see your breath on a winter day, all of these are the same phenomenon. Air cooling below its dew point, vapor becoming visible, the invisible made manifest. But here's something fascinating. The air doesn't simply decide on its own to cool down and spontaneously form a cloud. Something external has to lift it upward. Something has to carry it higher and higher into the cooler layers above where temperatures drop steadily with altitude. When air rises, when it climbs through the atmosphere like an invisible balloon, it expands naturally, inevitably, because the pressure around it decreases with altitude. Think about it. There's less air pressing down from above as you go higher, so the air parcel spreads out, relaxes, expands. It's like opening a vacuum-sealed bag. The moment you break the seal and reduce the pressure, everything inside immediately expands to fill more space. The same thing happens to rising air. As it climbs higher and the pressure decreases, it naturally expands. An expansion, you see, takes energy, quite a bit of energy actually. That energy must come from somewhere, and it's borrowed, taken directly from the air's own internal warmth, its own heat content. As a result, as a natural consequence of this expansion, the air cools as it climbs. This beautiful, elegant process is known as adiabatic cooling. Adiabatic, a wonderful word from Greek, meaning impassable, referring to the fact that no heat is added or removed from the outside. All the cooling comes from within. Think of it, if you will, as the atmosphere's version of decompressing after a very long, exhausting day at work. It stretches out its invisible limbs, relaxes deeply into the space around it, and quite literally chills out. The rate at which unsaturated air cools as it rises is remarkably consistent, about 10 degrees Celsius for every kilometre of altitude gained, nearly 3 degrees Fahrenheit for every 1,000 feet. It's one of those wonderfully reliable constants in an otherwise chaotic atmosphere. You can count on it, depend on it, use it to predict when and where clouds will form. There are many gentle, subtle ways this lifting happens throughout the day and night, all across our planet. Sometimes, on a bright summer morning, the sun warms the ground below with its golden rays. Dark soil, asphalt parking lots, rocky hillsides, they all absorb this solar energy differently, creating patches of warmth scattered across the landscape. And pockets of air sitting right above these warm patches begin to rise in lazy, spiraling columns, thermal updrafts, invisible elevators of warmth that form those cottony, fair-weather clouds we love to watch on peaceful summer afternoons. You can actually see this process if you watch birds carefully. Hawks and eagles, those magnificent gliders, know all about thermals. They spiral upward on these invisible columns of rising warm air, gaining altitude without flapping their wings, riding the same currents that will later form clouds. When you see a bird circling and climbing without apparent effort, you're watching it surf a thermal, and if conditions are right, if the air is humid enough, a cloud will form at the top of that same thermal within the hour. Other times, mountains force air upward as winds blow steadily against their slopes, pushing the air up and over, like water flowing over a dam. As this air climbs the mountainside, it cools and wrings out its moisture as delicate mist clinging to the peaks and shoulders, creating those mysterious ethereal clouds that seem to pour down mountain slopes like ghostly waterfalls. This is called orographic lift, from the Greek words for mountain writing, because mountains literally write clouds into the sky. Some of the world's wettest places are mountain slopes that face prevailing winds. The Olympic Peninsula in Washington state, the Western Ghats in India, the windward sides of Hawaiian Islands, all receiving hundreds of inches of rain per year, because mountains force air upward, cooling it, and wringing out its moisture day after day after day. Along weather fronts, those vast boundaries where different air masses meet and collide, warm air is gently pushed up and over heavier, denser cold air, forming massive sheets of layered clouds that can stretch for hundreds upon hundreds of kilometers across the sky, covering entire states, entire countries sometimes. Even a city skyline with its concrete and steel, or a dense forest canopy with its millions of leaves, can nudge air upward just enough to make a faint haze appear in the distance on a humid day. Cities, in particular, create their own little microclimates. The urban heat island effect, where concrete and asphalt absorb and re-radiate heat, can generate enough rising air to trigger cloud formation and even thunderstorms on humid summer days. Some cities actually see more rain downwind of their urban centers because of this effect. Once the air reaches its dew point at last, once it finally crosses that invisible threshold we talked about earlier, something truly remarkable, something almost magical, happens. The water vapor doesn't just spontaneously turn into droplets out of thin air, appearing like some sort of conjuring trick. No, it needs something to cling to, tiny surfaces, microscopic platforms on which to gather and slowly grow. These are called aerosols, and they're absolutely everywhere in our atmosphere. Microscopic particles of salt from ocean spray, blown high into the air when waves crash and bubbles burst. Each breaking wave sends thousands of tiny droplets into the air, and when these droplets evaporate, they leave behind microscopic salt crystals perfect seeds for cloud droplets. Dust lifted from distant deserts, sometimes traveling thousands of miles across continents and oceans. Saharan dust regularly crosses the Atlantic Ocean all the way to South America. Dust from the Gobi Desert can travel across the Pacific to North America. These tiny particles, smaller than a grain of sand, smaller than a particle of pollen, drift on winds for weeks, waiting to become the heart of a cloud droplet. Pollen released from flowers and trees during spring and summer, smoke from wildfires, volcanic ash from eruptions, even tiny fragments of meteorites that have burned up in the upper atmosphere. Industrial pollution, unfortunately, also provides countless aerosol particles, soot from combustion, sulfates from power plants, nitrates from vehicles, even living things, bacteria and fungal spores can serve as cloud condensation nuclei. Around each one of these infinitesimally small particles, each speck smaller than a bacterium, a droplet slowly, carefully forms and grows. Water molecules gather, one by one, attracted to the particle's surface, building up layer by microscopic layer. The process is surprisingly selective. Water vapor doesn't condense equally well on all surfaces. Some particles, especially salt, are hygroscopic, meaning they attract water readily. A salt crystal can start gathering water even before the air reaches 100% relative humidity. Other particles, like dust or soot, are less effective, requiring higher humidity levels before condensation begins. This is why clouds can form more easily over oceans, where salt particles are abundant, than over dry continental interiors where aerosols might be scarce. It's also why pollution can actually make clouds more numerous, though often composed of smaller droplets, because it provides so many extra condensation nuclei. A typical cloud droplet is only around 10 micrometers across, 10 millionths of a meter, so incredibly, impossibly small that it would take about 100 of them, lined up side by side like tiny pearls on a string, just to span the width of a single human hair. And in every cubic centimeter of a cloud, a space no larger than a sugar cube you'd drop in your coffee, there might be hundreds upon hundreds of these droplets, sometimes even thousands, all suspended together in perfect balance, too small and light to fall to the ground, but large enough, just barely large enough to scatter sunlight in every direction and appear to us as white glowing mist. To give you some sense of scale, if a cloud droplet were the size of a marble about 2 centimeters across, a raindrop would be the size of a beach ball, 60 centimeters wide. That's how much these droplets need to grow before they can fall as rain. They need to increase their size by a factor of about 100, their volume by a factor of 1,000,000. From a distance, from where we stand on the ground looking up, this entire intricate process looks utterly effortless. A gentle puff simply drifting into view, appearing out of nowhere, as if by magic or divine intervention. But within that puff, within that soft, innocent appearance, physics is incredibly busy at work, orchestrating an invisible symphony of molecular interactions. The newly condensed droplets, as they form from vapor to liquid, release tiny amounts of heat. This phenomenon is called the latent heat of condensation, and it's one of the atmosphere's most important energy sources. This released warmth, this liberated energy, slightly heats the surrounding air, giving it extra buoyancy, helping it rise just a little bit higher still into the cooler air above. This feedback mechanism fuels the cloud's continued growth, like a soft, invisible engine powered entirely by temperature differences and the endless dance of phase changes between liquid, vapor, and ice. Think about what's happening here. When water evaporates from the ocean or a lake, it absorbs energy, taking heat from its surroundings. This is why evaporating sweat cools your skin, but when that vapor later condenses back into liquid droplets in a cloud, it releases that same energy. The heat that was absorbed at the surface is now being released high in the atmosphere. This is how clouds become engines of energy transport. They move heat from the surface, where the sun is warming things up, to higher altitudes, where the atmosphere is cooler. A single tropical thunderstorm can release as much energy through condensation as a small nuclear bomb. That's how powerful this process is. And so, the cloud expands slowly upward and outward, layer upon gentle layer, breath upon breath, until its base, its flat, remarkably well-defined bottom, marks the precise level where the air first became saturated with moisture. You can actually see this threshold with your own eyes on a humid summer day if you know what to look for. Watch the horizon carefully, patiently. Notice how remarkably, impossibly flat the base of a cumulus cloud appears. That clean line stretched across the sky like it was drawn with a ruler is called the lifting condensation level. It's an invisible boundary, a demarcation line, where vapor gives up its invisibility and becomes something we can finally see with our naked eyes. Below that line, the air remains unsaturated, still capable of holding more moisture and perfectly clear, allowing light to pass through unobstructed. Above it, the sky turns milky white with billions upon billions of suspended droplets, each one catching and scattering the sunlight. It's as though the atmosphere drew a perfect, ruler straight line across the endless sky and announced clearly, right here, at this precise altitude, this is where the visible world begins. On days when multiple cumulus clouds are scattered across the sky, notice how they all share the same base altitude. They all sit on the same invisible shelf. This is because they're all forming in the same air mass, with the same temperature and moisture profile. The lifting condensation level is the same throughout the region. It's one of the most beautiful demonstrations of atmospheric physics you can witness with just your eyes and patience. The same beautiful transformation plays out much closer to the ground as well, in ways we experience every day without realizing it. On a cool morning in autumn or winter, when frost touches the grass and the world feels crisp and new, your very breath meets the chilly air around you and turns instantly into a fleeting little cloud. That visible mist you see, that fog curling and dancing from your lips, isn't actually steam in the true scientific sense. True steam, pure, genuine steam, is completely invisible to the human eye. What you're seeing are tiny water droplets formed when the warm, moist air from deep within your lungs, air heated to your body temperature of about 37 degrees Celsius, cools rapidly upon contact with the cold morning air outside. The same thing happens when a kettle whistles cheerfully on the stove, or when you see mist curling gracefully above a lake at dawn, rising like spirits from the water's surface. It's water performing its favorite magic trick, its signature illusion, showing up unannounced whenever the air gets just cool enough to trigger the transformation. Morning fog over a lake is particularly beautiful to watch if you're ever fortunate enough to witness it, as the night cools the air near the water surface, but the water itself remains relatively warm from absorbing sunlight all day. The contrast creates perfect conditions for fog formation. The water evaporates moisture into the cool air above it, that air becomes saturated, and tiny droplets form right at the surface. The fog rises and swirls in ghostly patterns, dancing with the slightest breeze, creating an ethereal landscape that seems to belong to another world. If you could somehow drift through a newly formed cloud yourself, floating weightlessly through its soft, pillowy interior like an astronaut in zero gravity, you might expect to feel instantly wet, drenched even, soaked to the bone, but you'd hardly notice anything at all, really. The droplets are far too small and far too spread apart to soak you or even make you feel damp. The air inside a cloud is actually just as dry as the air outside of it in terms of relative humidity. Saturated, yes, at 100% relative humidity, but not dripping or wet in any tangible way. Mountain climbers and pilots who regularly pass through clouds report this exact experience. You might feel a slight coolness, a faint dampness, but nothing like walking through rain. It's more like walking through a very light mist. The cloud doesn't cling to you. It doesn't soak through your clothes. It just surrounds you, making everything look grey and formless until you emerge on the other side. You'd find yourself surrounded by millions upon millions, perhaps even billions, of tiny spheres, each one glinting faintly with refracted sunlight, each one moving gently, gracefully with the wind currents, occasionally colliding softly with others in their random dance, sometimes merging together upon contact into slightly larger drops that might, one day soon, grow heavy enough to fall to earth as rain. The interior of a cloud is not still or static. There's constant motion, updrafts carrying new moisture upward, downdrafts pulling drier air downward, turbulent mixing at the edges, where cloudy air meets clear air, droplets forming, growing, evaporating, reforming. It's a dynamic, living system, constantly in flux, never the same from one moment to the next. From a purely scientific perspective, from the view of atmospheric physics, the birth of a cloud is simply the atmosphere's elegant, efficient way of maintaining thermal balance across the planet. When warm, moist air rises from the surface, from sun-heated oceans or tropical rainforests, it redistributes heat vertically through the atmosphere, through the twin processes of condensation and convection. This fundamental process moves enormous amounts of energy from the warm surface below to the cooler layers high above, fueling vast weather systems, driving hurricanes and monsoons, and sustaining the global circulation of air that wraps around our entire planet like an invisible conveyor belt. Every cloud you see, no matter how small or seemingly insignificant it might appear, no matter how fleeting its existence, is part of that invisible atmospheric machinery that keeps Earth's climate stable, predictable, and habitable for all life. Consider this. Without this vertical transport of heat, without clouds moving energy upward through the atmosphere, the equatorial regions would be unbearably hot, and the poles would be even colder than they already are. The temperature gradient between equator and poles would be so steep that weather patterns would be far more violent than they are now. The gentle cloud you see drifting overhead on a summer day is actually part of Earth's global thermostat, part of the mechanism that keeps our planet livable. And yet, for something so common, so utterly ordinary and everyday, clouds remain deeply, profoundly personal to those of us who pause to watch them. They shape the quality of light during our days and the moods of our skies in ways we feel but rarely articulate. They're the subtle difference between a washed-out noon that feels harsh and oppressive and a golden sunset that takes your breath away and stops you in your tracks. A passing cloud can dim the sun just enough for you to notice, to actually feel on your skin. The warmth fade gently away, leaving a brief coolness in its wake. Or it might position itself just right, at just the perfect angle, to make a rainbow appear suddenly in the distance, a brilliant arc of color, a gift of light and water painted across the sky. In their simplest form, yes, clouds are condensed vapor, nothing more than water in a different state of matter. Thorough molecules clustered together instead of dispersed, but in their quiet, profound way, in the way they touch our hearts and imaginations, they're also emotion, reflection, and memory, all suspended beautifully in air. Perhaps that's exactly why people throughout all of human history have always seen more than mere physics in clouds. Poets and dreamers see boundless imagination floating overhead, inspiration made visible. Farmers and sailors see forecasts and predictions written in vapor, ancient wisdom passed down through generations. Children lying in the grass see animals, ships, dragons, and castles drifting lazily by, their shapes constantly morphing and changing, and scientists, looking closer still with their sophisticated instruments and elegant equations, see the precise, beautiful interplay of thermodynamics and fluid motion that makes all of it, every single bit of it, possible. There's a Japanese concept called kumugata, the shapes of clouds, which refers to the practice of finding meaning and beauty in their ever-changing forms. For centuries, artists and poets have contemplated clouds as symbols of impermanence, of the transient nature of all things. What is here now will soon be gone. What seems solid is really ephemeral. What appears permanent is constantly changing. Every cloud, no matter how ordinary or common it may seem, began with a simple moment of cooling, a parcel of air rising on invisible currents, expanding gently in the thinning pressure and reaching that precise critical point where it could no longer stay invisible. It's a powerful reminder, if we choose to see it this way, if we open ourselves to the lesson that even the most delicate, ephemeral wonders in our world start from change, from transformation. Warm breath meeting cool night air and becoming visible fog, vapor turning slowly, molecule by molecule to mist. The world quietly showing us that sometimes, just sometimes, to become visible, to become real and tangible, all you need to do is let go of a little heat. And perhaps there's a metaphor there for our own lives. Sometimes we need to rise above our familiar surroundings, to expand into new spaces, to cool our heated thoughts before we can transform into something new, before we can condense our scattered ideas into something visible, something real, something that others can see and appreciate. But I digress. Let us continue our journey upward into the organized world of cloud classification, where scientists have spent centuries trying to bring order to the chaos of the sky. The Great Cloud Atlas. Long before satellites circled overhead, capturing images every few minutes, before radar stations dotted the landscape tracking storms, before weather stations with their precise thermometers and barometers, people looked to the sky and learned its language through patient observation. They watched carefully, day after day, season after season, how clouds moved and changed, how they rose and fell with the rhythms of weather. And from that simple, careful observation, from centuries of watching the sky, they built entire systems of knowing when to plant the seeds in spring, when to harvest the crops in fall, when to take shelter from approaching storms. The sky, after all, was their first teacher, their most reliable guide, their constant companion. Farmers in ancient times could predict weather with remarkable accuracy simply by reading clouds. They knew that certain patterns meant rain was coming, other patterns meant fair weather would continue. Still others warned of dangerous storms approaching. This knowledge was passed down through generations, encoded in folk sayings and weather proverbs that we still remember today. Red sky at night, sailors delight. Red sky at morning, sailors take warning. Mackerel sky, never long wet, never long dry. These weren't just cute rhymes, they were condensed meteorological wisdom. For something that seems endlessly changeable, infinitely variable, the sky actually follows a quiet underlying order. Every shape of cloud you've ever seen, from a paper-thin veil barely visible against the blue to a towering anvil reaching into the stratosphere, belongs to a great atmospheric family. They are categorized and classified not by whim or poetry, not by artistic interpretation, but by how high they live in the atmosphere and how they move and behave. Learning their names and characteristics is like learning the language of the air itself, a way to read the mood of the sky, to predict what might come next, all at a single glance upward. The modern naming system we use today dates back to the early 19th century, a time of great scientific classification and organization, when a British pharmacist and passionate amateur meteorologist named Luke Howard decided that the heavens themselves deserved some systematic organization. Instead of calling them fluffy thing number 2, or that grey one, or the one that looks like a horse galloping across the sky, he used Latin, because of course he did. Everything sounds more elegant, more scientific, more timeless in Latin. His simple but utterly brilliant idea was to classify clouds by both their physical form and their altitude in the atmosphere. Luke Howard presented his classification system in a lecture to the Askesian Society in London in December 1802. It was a relatively obscure gathering. Not many people attended, but the impact of his ideas would ripple across centuries. He proposed just 3 basic categories: cirrus, cumulus, and stratus, and a 4th term, nimbus, for rain-bearing clouds. From these simple building blocks, he could describe virtually every cloud in the sky by combining terms. The system was elegant in its simplicity, revolutionary in its practicality, and remarkably, it's still the foundation of cloud classification today, more than 200 years later. Scientists have added refinements, subcategories, new species and varieties, but Howard's basic framework remains intact. Those Latin roots, those ancient word fragments, have survived ever since Howard first proposed them in 1802, turning everyday weather into something that feels almost classical, almost poetic. At the broadest level, there are 3 main fundamental forms that clouds take. Cumulus, which comes from the Latin word meaning heap or pile. These are the clouds that build vertically, that stack upward like cottony towers. Stratus, from the Latin meaning layer or blanket spread across the sky. These are the horizontal clouds, the ones that spread out in sheets. And cirrus, meaning curl or wisp or lock of hair, describing their delicate feathery appearance. These are the high, thin, ice crystal clouds that look like brush strokes across the sky. The 4th term, nimbus, is actually a modifier, an addition, used when a cloud is actively producing rain or snow, turning from decoration into precipitation. Any cloud can potentially become a nimbus cloud if conditions are right. A cumulus can become a cumulonimbus. A stratus can become a nimbostratus. The prefix or suffix nimbus simply tells you that it's raining or snowing from that cloud right now. These forms describe the appearance and behavior of clouds, whether a cloud heaps up vertically, spreads horizontally, or threads delicately across the sky, while their altitude bands, their height ranges, define their homes in the atmosphere: low, middle, or high. Add a few prefixes and suffixes to combine these ideas, and suddenly you have the entire atmospheric family tree, a complete taxonomy of the sky. The atmosphere itself is divided into layers, and clouds respect these boundaries. They form at different altitudes depending on temperature, moisture availability, and atmospheric stability. Understanding these altitude bands helps us read what's happening at different levels of the atmosphere just by looking up. Low-level clouds usually live and form from the surface up to around 2 kilometers high, roughly 6,500 feet. These include stratus, stratocumulus, and the lower, developing forms of cumulus. These are the clouds you're most likely to touch if you climb a small mountain or fly in a small aircraft. They're the clouds that bring us most of our day-to-day weather, our drizzle and light rain, our overcast skies, and partly cloudy afternoons. Stratus are the blanket clouds, the ones that make everything grey. Flat, uniform grey layers that cover the entire sky, like a thick comforter pulled tight from horizon to horizon. They often bring drizzle, that fine, persistent rain that seems to hang in the air, or at least the heavy feeling that drizzle might start at any moment. Though the clouds never quite make up their minds, on a stratus day, the world feels muted, sounds seem dampened, colours appear washed out. The horizon disappears into a featureless grey. It's not dramatic weather, not exciting or dangerous, just persistently dreary, but there's a certain calm to it too, a certain peace. The world feels quieter under a stratus blanket, gentler, softer. Stratus clouds form when moist air rises gently over cooler air in stable atmospheric conditions, creating uniform sheets instead of the bubbling vertical towers of convection. They're common after rain systems pass through, when the atmosphere is stable and moisture-laden but lacking the energy for more dramatic cloud formation. They're also common in coastal regions where marine air moves onshore, bringing its moisture, but not enough instability for towering clouds. Stratocumulus, their more textured, more interesting cousins, have a bit more personality, a bit more character. They appear as lumpy grey rolls or patches that may stretch from horizon to horizon like an endless cobblestone road in the sky, often breaking apart in places to reveal tantalizing slivers of blue between the grey. They mark the subtle transition between calm, stable skies and convective, unstable skies, neither fully one nor the other, neither fully stable nor wildly unstable. If you look carefully at stratocumulus clouds, you'll notice they have a wonderful texture. They're not flat and featureless like stratus. Instead, they show clear signs of organization, rolls and waves and cells. This texture reveals the gentle mixing happening in the lower atmosphere. Weak updrafts create the lighter, whiter patches. Weak downdrafts create the darker areas where you can see through to clearer air or higher cloud layers. They're the compromise clouds, the middle ground clouds, happy to just hover and exist, without too much drama or spectacle. Stratocumulus days are neither gloriously sunny nor thoroughly miserable. They're just there, existing, doing their job of regulating temperature and reflecting some sunlight without producing any precipitation. Cumulus are undoubtedly the crowd pleasers, the stars of the cloud world. These are the puffy, brilliant white heaps that children draw instinctively, automatically when they imagine the sky, when they're asked to draw a cloud in art class. They form from rising thermals of warm air that cool and condense into soft cotton-like shapes that seem almost edible, almost good enough to eat, like meringues floating in a blue bowl. On most fair-weather days they stay modest and well-behaved, scattered across the sky like sheep grazing in a blue meadow, their flat bases all neatly aligned at exactly the same altitude, the lifting condensation level we discussed earlier, as if they're all sitting on an invisible shelf. This creates one of the most pleasing sights in nature, a blue sky dotted with puffy white clouds, all hovering at the same height, all casting similar shadows on the ground below. Fair-weather cumulus have a life cycle you can watch if you're patient. They form in late morning as the sun heats the ground. They grow through midday, and they often dissipate in late afternoon as the sun's heating diminishes and the atmospheric instability decreases. Each cloud might last only 10 or 15 minutes, forming, existing, then evaporating, replaced by another cloud forming nearby. It's a constantly refreshing display, but given enough heat from the sun and enough moisture in the air, cumulus can grow ambitiously upward into cumulus congestus, towering heaps that reach for the sky, or even transform completely into cumulonimbus, the massive towering thunderclouds that dominate entire skylines and command respect from anyone who sees them approaching. We'll talk more about these dramatic transformations later. For now, just know that the innocent cumulus you see on a summer morning might be the seed of an afternoon thunderstorm. Mid-level clouds, found between about 2 and 6 kilometers up in the atmosphere, roughly 6,500 to 20,000 feet, include altostratus and altocumulus. These clouds inhabit the middle realm, not quite ground level but not yet in the thin, cold air where ice crystals dominate. They're composed of water droplets, ice crystals, or more commonly a mixture of both, depending on the temperature at their altitude. The prefix alto comes from Latin meaning high, though ironically these aren't actually the highest clouds. When Luke Howard and his successors were naming clouds, they considered anything above the low-level clouds to be high. Later, when even higher clouds were recognized as a distinct category, they needed a new name and chose Suro for the truly high clouds. But by then alto was already established for the middle level. Altostratus clouds are thin greyish veils that often dim the sun without completely hiding it, creating that peculiar effect where you can sometimes see the sun's position as a brighter spot behind the clouds, like a lamp behind frosted glass. They frequently signal an approaching change in weather, often appearing hours or even a day ahead of warm fronts that will eventually bring steady rain to the region. When you see alta stratus moving in, especially if they're thickening and lowering, it's time to think about bringing in lawn furniture or planning indoor activities. Rain is likely within 12 to 24 hours. Meteorologists call these precursor clouds the advance guard of a weather system. They're part of the broad, elevated shield of clouds that extends hundreds of kilometers ahead of a warm front. The sun through altostratus has a distinctive appearance. It's visible but diffuse, like looking at a light through wax paper. You can look in its general direction without squinting painfully. The whole sky takes on a uniform grey-white glow. Some people find it oppressive, others find it peaceful. There's no harsh shadows, no glare, just soft, even light from horizon to horizon. Altocumulus are small, patchy formations that can look like fish scales or fleecy rows when viewed from below, sometimes called a mackerel sky because they resemble the patterns on a mackerel's back. These clouds often form from gentle waves of air rippling through the middle atmosphere like invisible ocean swells, and their presence tells experienced weather watchers that moisture and atmospheric instability are quietly increasing, that change may be coming soon. The wave-like patterns in altocumulus are fascinating to watch. They reveal gravity waves in the atmosphere, oscillations where air moves up and down like water waves moving across the ocean. When air is forced upward by these waves, it cools and forms cloud. When it descends, the cloud evaporates. The result is these beautiful parallel rows of clouds that can stretch from horizon to horizon. Morning altocumulus, especially the variety called altocumulus castellanus, that has turret-like towers on top, often predict afternoon thunderstorms. The towers show that the middle atmosphere is becoming unstable. If the lower atmosphere heats up during the day, that instability can extend down to the surface, and storms can develop. So that pretty mackerel sky at sunrise might be a warning that you should carry an umbrella. Higher still, in the cold and rarefied air, above 6 kilometers, above 20,000 feet, where the air is thin and temperatures drop far below freezing, are the magnificent cirrus clouds. These are the wisps, streaks, and delicate feathers of pure ice crystals that drift near the top of the troposphere. At these altitudes, temperatures are typically minus 40 degrees Celsius or colder. All water exists as ice. Liquid droplets cannot survive. Cirrus clouds often appear hours or even days before a significant change in weather, stretched into long, elegant filaments by the strong upper-level winds of the jet stream. The jet stream, those rivers of fast-moving air that flow from west to east at high altitudes, can reach speeds of 200 or even 300 kilometers per hour. Cirrus clouds caught in these winds get stretched and pulled into long streaks called mare's tails, named for their resemblance to a horse's flowing tail. They can be as delicate as silk threads, as fine as angel hair, catching the last golden light of the day in brilliant reds, oranges, and golds long after the sun has set below the horizon for those of us on the ground. This happens because cirrus clouds are so high that they remain in sunlight even after the sun has dipped below the horizon from our perspective at ground level. They glow like embers in the darkening sky, a final farewell from the departing day. Because they are composed entirely of ice rather than liquid water, their tiny crystalline fibers sometimes scatter and refract light in spectacular ways, producing halos around the sun or moon, and sundogs, those mysterious colored spots that appear on either side of the sun, tiny rainbows that shimmer and dance in the high, frozen air. A 22-degree halo around the sun or moon is one of the most common ice crystal phenomena. It appears as a ring of light, sometimes faintly colored with red on the inside and blue on the outside, at an angular distance of 22 degrees from the sun or moon. This specific angle comes from the geometry of hexagonal ice crystals and how light refracts through them. Sundogs, also called parhelia, appear as bright spots 22 degrees to the left and right of the sun when it's low in the sky. They're often more colourful than halos, showing distinct red, yellow and blue. On rare occasions when atmospheric conditions are perfect, you might see the halo and two sundogs simultaneously, creating a stunning display of atmospheric optics. When these high and low forms mix and combine, when different levels interact, we get fascinating hybrids and variations. Cirrostratus, cirrocumulus, altostratus, altocumulus, stratocumulus. Each name is a combination of two Latin clues, two descriptive fragments. One fragment describing the basic shape and structure, the other describing the approximate height or altitude where they form. Cirrostratus, for instance, are the thin, almost transparent icy veils high in the atmosphere that can produce those beautiful halos around the moon on clear nights. They're often so thin you barely notice them, just a slight milkiness to the sky. But when you see a halo around the moon, you know cirrostratus is present even if you can't see the clouds themselves. They're like invisible curtains that reveal themselves only through their interaction with light. Stratocumulus beautifully blend the horizontal layering of stratus with the vertical puffiness of cumulus, forming quilt-like patterns that ripple gently across the lower sky. They're probably the most common cloud type over many parts of the world, especially over oceans. They're stable enough to persist for days, but textured enough to be visually interesting. The World Meteorological Organization, the international body that standardizes weather observations, recognizes 10 basic cloud genera. These are cumulus, stratus, stratocumulus, nimbostratus, altostratus, altocumulus, cirrus, cirrostratus, cirrocumulus, and cumulonimbus. From these 10 basic types, there are species and varieties that describe specific characteristics. Clouds can be fractured, lens-shaped, towering, flattened, fibrous, and dozens of other descriptive terms. Then there are the rainmakers, the active clouds, the clouds with purpose. Nimbus, meaning cloud or rainstorm in Latin, turns an ordinary passive formation into something active and productive. Nimbostratus are thick, dark grey blankets that pour steady, persistent rain or snow, the kind that can linger stubbornly for an entire afternoon or even days, soaking everything below. Nimbostratus lack the dramatic vertical development of thunderstorms. They're not exciting. They don't produce lightning or hail or damaging winds. They just rain and rain and rain. Grey, heavy, and relentless. The kind of weather that makes you want to stay inside with a book and a cup of tea. These clouds form in stable atmospheric conditions where moist air is being lifted gradually over large areas, typically along warm or occluded fronts. The lifting is gentle but persistent, wringing out moisture through a deep layer of the atmosphere. The result is a thick layer of cloud that can extend from near the surface up to 6 kilometers or more in altitude. The rain from nimbostratus is steady and moderate, rarely heavy enough to cause flooding, but persistent enough to accumulate significant totals over hours or days. It's the kind of rain that farmers appreciate, soaking deep into the soil, rather than running off, the kind that fills reservoirs and recharges groundwater. Cumulonimbus are the true giants, the towering thunderheads that inspire awe and sometimes fear. Immense vertical structures that reach from low levels near the ground all the way up to the tropopause, sometimes 15 kilometers high, nearly 50,000 feet, higher than most commercial aircraft fly. Within their massive bodies, air churns violently upward and downward at tens of meters per second, powerful enough to tear apart any aircraft foolish enough to enter, generating lightning that lights up the sky, thunder that shakes windows, and hail that can damage crops and cars. A fully developed cumulonimbus is arguably the most powerful and beautiful cloud formation in Earth's atmosphere. It combines the vertical development of cumulus with the precipitation production of nimbus clouds, but on a scale that dwarfs either parent type. A single large cumulonimbus can contain 1,000,000 tons of water. It can generate wind gusts exceeding 100 miles per hour. It can produce hailstones the size of baseballs. It can spawn tornadoes that devastate entire communities. From the outside, viewed from a safe distance, they appear majestic, powerful, even strangely peaceful in their grandeur. The massive anvil top spreading out for dozens of kilometers, the dark, threatening base, the occasional flicker of lightning illuminating the interior, the whole structure rotating slowly. If it's becoming a supercell, it's beautiful in the way a volcano or a hurricane is beautiful, powerful, and dangerous, but undeniably magnificent. But within them lies one of nature's most powerful, most violent engines of energy release. We'll explore the interior world of cumulonimbus more deeply in the next section. For now, just appreciate that this cloud, this single atmospheric phenomenon, can release as much energy in an hour as a small nuclear weapon, and it does so through nothing more than water changing phase and air moving vertically. The form of each cloud, its ultimate shape and appearance, is determined entirely by physics, by the delicate balance between rising motion, available moisture, and the stability profile of the air. Flat, horizontal layers mean air is lifting slowly and evenly across a broad area. Vertical towers mean it's rising fast and forcefully in concentrated updrafts. Puffy, distinct clouds form where the atmosphere encourages localized upward motion. Smooth, sheet-like ones form where the atmosphere resists and suppresses vertical development. Even the edges of clouds tell their own story to those who know how to read them. Crisp, sharp, well-defined outlines reveal strong updrafts, an active condensation happening right at the cloud's boundary. The updraft is strong enough to push the cloud edge outward faster than it can evaporate. The result is a sharp, crisp outline, the kind you see on fresh cumulus clouds on a summer afternoon, while frayed, soft, dissolving ones hint at dry air from the surroundings nibbling away at the cloud's sides through that process called entrainment, slowly eating away at the cloud from the outside in. Entrainment is the mixing of cloudy air with clear air at the cloud boundary. When dry air mixes into a cloud, some droplets evaporate. The cloud edge becomes fuzzy and indistinct. Eventually, if entrainment is strong enough, the entire cloud can evaporate from the edges inward. You don't need expensive instruments or sophisticated equipment to start reading the sky like a book. With just a bit of practice and patient observation, you can tell whether the day is warming or cooling, whether moisture is increasing or gradually fading away, whether storms are approaching or moving away, simply by watching carefully the texture, movement, and altitude of the clouds above you. A line of cumulus clouds growing steadily taller hour by hour means convection is strengthening, and afternoon storms might be developing. Watch the tops. Are they just rounded and puffy, or are they starting to tower upward, reaching for the sky? Are the edges sharp or fuzzy? Is lightning flickering in the distance? These signs tell you whether those innocent puffs are staying benign or transforming into something more serious. A spreading layer of thin cirrostratus, appearing around the sun like a veil, means a weather front may be on its way, perhaps arriving within 24 hours. The thicker the cirrostratus becomes, the lower the clouds that follow, the sooner the precipitation will arrive. It's like watching the advance guard of an approaching army. First the scouts appear, then more forces, then finally the main body. When clouds flatten out completely, or vanish altogether, it's a reliable sign that the atmosphere is stabilizing, that settled weather is likely. High pressure is building, sinking air is evaporating any clouds that try to form. Fair weather should continue for at least the next day or two. It's like reading a slow-moving diary, written continuously by air and light, updated moment by moment across the canvas of the sky. Once you learn the language, you can't help but read it. Every time you step outside, you glance up and automatically assess the sky. You notice the clouds, their type, their movement, their development. You make predictions about the coming weather without even thinking about it. On a lazy summer afternoon, when time seems to slow down and the world feels peaceful, you might lie back in a grassy field and watch the entire cloud family at work above you. Low, lazy cumulus drifts slowly by like white ships sailing on a calm, invisible sea. Higher up, barely visible, thin cirrus clouds trace the winding paths of invisible jet streams racing across the sky at hundreds of kilometers per hour. Occasionally, a translucent veil of altostratus slides quietly in from the west, softening the harsh brightness of the afternoon sun, making the light gentler, more diffuse. The entire sky is alive with motion and meaning, each level, each altitude, whispering its own unique version of the same fundamental story, airlifting upward on invisible currents, cooling as it rises, and turning its moisture into visible form, into art, into clouds. It's easy to understand why people throughout history, in every culture and civilization, look to the heavens for signs and omens, for guidance and wisdom. The patterns above us are not random at all, not chaos or chance. They're the visible handwriting of the atmosphere, the sky's way of communicating, of telling us what's happening and what might come next. And though Luke Howard gave them formal Latin names more than 2 centuries ago, though science has explained their physics in exquisite detail, their beauty still needs no translation, no explanation. It speaks directly to something deep within us. Different cultures have developed their own relationships with clouds. In Japan, cloud appreciation is considered a refined aesthetic pursuit. In indigenous Australian cultures, cloud formations are part of weather lore passed down through countless generations. In maritime cultures worldwide, clouds have always been essential for navigation and survival at sea. So the next time you find yourself gazing upward, taking a moment from your busy day, try naming what you see. Cirrus for the high, delicate streaks, stratus for the low, grey blankets, cumulus for the puffy white heaps, and nimbus when you feel the first drops of rain begin to fall on your upturned face. The language might sound ancient and formal, borrowed from a dead language spoken in ancient Rome, but it's really just Earth speaking in clouds, an endless, timeless conversation between sunlight, air, and water that anyone with a little patience and attention can learn to understand. From puff to power, every thunderstorm, every single one that has ever rumbled across the land, begins with something remarkably small and innocent. A single cottony puff, drifting lazily above a sun-warmed field on a summer afternoon. It looks harmless, even playful, like something a child might draw with crayons. But inside that soft, seemingly gentle shape, deep within its billowing white interior, a powerful engine is beginning to turn, to awaken, to gather strength. Air is rising faster than you could run, faster than you could drive a car on a residential street. Moisture is condensing by the ton, literally by the ton, every single second, and invisible drafts, unseen rivers of moving air, are building the foundations of a skyscraper in the sky, a tower you can't lease, an edifice made entirely of water and ice. The life of a cumulus cloud, from birth to maturity to dissolution, is fundamentally a story of growth. Quiet and gentle at first, then restless and turbulent, then magnificent and overwhelming, and finally, after its brief moment of glory, dissolution, and decay. It's a complete life cycle that can unfold in just a few hours, from first formation to final dissipation. The earliest stage begins innocently, with what meteorologists call a fair weather cumulus. These are the daytime dreamers of the sky, white puffy heaps floating lazily above perfectly flat bases that mark the lifting condensation level. They form when warm air near the surface, heated by the sun-baked ground below, rises gently, expands as pressure decreases, and cools to its dew point. At first, in these early moments of formation, the upward motion is gentle and unhurried, the kind of leisurely lift that might carry a bird on an easy glide, or a dandelion seed, floating slowly upward on a warm afternoon breeze, maybe 1 or 2 meters per second, barely a walking pace, nothing dramatic or intimidating. Inside the young cloud, microscopic droplets collide and occasionally merge, but the cloud itself remains shallow, modest, well-behaved, perhaps only a few hundred meters from base to top, small enough that you could hike its entire vertical extent in less than an hour if you could somehow walk straight up through the air. If you were to watch one closely for 10 or 15 minutes, really pay attention to its changing form, you'd see it constantly rebuilding itself from within, new wisps and tendrils forming continuously on top as fresh warm air arrives from below, while the lower parts fade and evaporate as they mix with drier air from the surroundings. It's a living structure, breathing in sunlight and warmth from below, breathing out vapor that returns to invisibility at its edges. The cloud is in a delicate balance. For every gram of moisture condensing at its top, another gram is evaporating at its sides and bottom. The cloud appears static when viewed as a whole, but it's actually in constant turnover. The water molecules within it are continuously cycling between vapor and liquid, joining the cloud, leaving the cloud, rejoining it elsewhere. But sometimes, on certain special days when conditions align just right, the conditions are perfect for ambition. If the air high above is unstable, if temperature decreases rapidly with height, and if the rising current of warm air is strong and persistent, the innocent puff refuses to stop climbing. As it rises higher and higher, the droplets within release their latent heat of condensation, giving the surrounding air extra buoyancy, extra lift, which helps it soar even higher still in a self-reinforcing feedback loop. This feedback is crucial to understanding how small clouds can grow into thunderstorms. Without it, most clouds would stay small. The latent heat release is what turns a modest cloud into a monster. Every kilogram of water that condenses releases about 2,500,000 joules of energy, enough to lift that kilogram of air up 250 kilometers. If all the energy went into lifting, of course, much of it goes into heating rather than lifting, but it's still a tremendous energy source. The result, the product of this runaway growth, is a cumulus congestus, a growing tower that begins to look less like a soft pillow and more like a column of white marble reaching upward toward the heavens. Updrafts inside this developing tower may reach impressive speeds of 5 to 10 meters per second, sometimes even faster, enough to hurl droplets upward faster than gravity can pull them down. To put that in perspective, 10 meters per second is about 22 miles per hour. That's fast enough to make walking difficult if you faced it as a headwind. And it's happening invisibly inside the cloud, lifting millions of tiny droplets, suspending them against gravity, building the tower higher and higher. From the ground below, watching this transformation unfold, it's a mesmerizing, almost hypnotic sight. The edges of the cloud boil and roll like water in a pot, like a living sculpture, constantly reshaping itself, as warm, moist air rushes in continuously from below to feed the growing monster. The top blossoms and billows upward, glowing brilliant, dazzling white against the deep blue of the sky. Each new burst of rising air adds another layer of cloud, another story to the tower, like bricks being laid one after another by invisible hands working at impossible speed. If you have time to watch, if you can sit and observe for an hour, you'll see the tower double its height, then triple it. The cloud that started as a modest puff a kilometer across and a kilometer tall might grow into a massive tower 5 kilometers across and 8 kilometers tall, all in an hour or two. The architecture of the cloud becomes more defined with each passing minute, more impressive, its vertical reach more daring and ambitious with every moment. It's a slow-motion construction project unfolding before your eyes, powered entirely by nothing more than sunlight warming the earth below. No engines, no machinery, just thermodynamics and phase changes, just air and water, doing what they naturally do when conditions are right. Eventually, if conditions continue to support its growth, the tower climbs high enough to reach what's called the freezing level, the altitude where the temperature drops below 0 degrees Celsius, below 32 degrees Fahrenheit. Here, in this colder realm miles above the Earth, the tiny water droplets begin their transformation to freeze into tiny, delicate ice crystals. And this freezing process, this phase change from liquid to solid, releases yet more latent heat into the surrounding air, heat that fuels the updrafts even further, pushing them to even greater speeds and heights. The freezing level is typically around 3 to 5 kilometers above the surface in mid-latitudes during summer, lower in winter, or at higher latitudes, higher in the tropics. When a growing cumulus cloud reaches this altitude, its character begins to change. The smooth, cauliflower-like top starts to develop a more fibrous, wispy appearance as ice crystals form. The cloud, now tall enough to pierce multiple distinct layers of the atmosphere, now reaching heights where commercial airliners cruise, enters its next developmental stage. Cumulus calvus, a cloud whose once smooth, rounded top begins to lose its soft, well-defined outlines, turning fibrous, wispy, and blurred at the edges. Calvus, a wonderful Latin word meaning bold, an oddly appropriate, almost humorous term for a cloud, shedding its smooth appearance as ice takes hold in its upper reaches. The transformation is visible, if you watch carefully. The sharp, crisp edges that defined the young cumulus begin to soften. Streaks of ice crystals start to extend from the top, giving it a slightly fuzzy or hairy appearance. The brilliant white of water droplets begins to mix with the more translucent appearance of ice. The cloud is transitioning from a purely liquid droplet cloud to a mixed phase cloud containing both liquid and ice. As the cloud keeps climbing relentlessly, driven by powerful updrafts that refuse to quit, it may eventually reach the upper limits of the troposphere itself, around 10 to 15 kilometers high, anywhere from 30,000 to 50,000 feet. The air here at these extreme heights is thin, bitterly cold, and remarkably stable, forming a kind of invisible ceiling, an atmospheric boundary called the tropopause. The tropopause is one of the most important boundaries in our atmosphere. Below it, in the troposphere, temperature generally decreases with height. Above it, in the stratosphere, temperature actually increases with height. This temperature inversion creates an extremely stable layer, a cap that resists vertical motion. It's why clouds stop growing when they reach it. The stratosphere doesn't want rising air, it pushes back. When the rising cloud finally hits this barrier, when it reaches this atmospheric ceiling, it can no longer rise freely upward. The stable stratosphere above simply won't allow it. Instead, having nowhere else to go, the cloud spreads outward horizontally, expanding sideways across the sky, forming the signature flat, anvil-shaped top of a mature cumulonimbus, the most powerful cloud formation in Earth's atmosphere. This spreading process happens relatively quickly. Within minutes, what was a vertical tower begins to flatten at the top. The expanding ice crystals spread outward like cream poured into coffee, creating a vast shield that can extend 50 or even 100 kilometers from the main updraft. The anvil is born. The Latin name for this final mature stage, capillatus, comes from a word meaning hairy, referring to the wispy, hair-like icy filaments that drift and stream from its crown like banners in the high-altitude winds. It is both stunningly beautiful and utterly formidable at the same time, a monument of condensation, sculpted entirely by the elegant, unbreakable laws of thermodynamics. From the ground, a mature cumulonimbus with its anvil top is an unmistakable sight. The dark, threatening base, the towering vertical column, the flat, spreading anvil that seems to dominate half the sky. It's both beautiful and ominous, magnificent and frightening. Everyone who sees it knows instinctively something powerful is happening, something that demands respect. Inside this immense structure, within this towering giant that may contain millions of tons of water and ice, chaos reigns supreme, powerful updrafts racing upward at speeds that would rip apart any aircraft foolish enough to enter, hurl droplets and ice pellets skyward with tremendous force. Speeds can exceed 30 meters per second, nearly 70 miles per hour, in the strongest updrafts of severe thunderstorms. That's hurricane force wind, but pointing straight up. While simultaneously, powerful downdrafts, cooled by evaporating rain, drag cooler air back down toward the surface with equal violence. These downdrafts can also reach 30 meters per second or more. Air rushes downward, accelerating as it falls, spreading out when it hits the ground in powerful gusts that can topple trees and damage buildings. The interior of a cumulonimbus is a three-dimensional battlefield. Updrafts and downdrafts coexist, sometimes separated by only a few kilometers horizontally. Air is being violently recycled, carried upward in the updraft, then downward in the downdraft, then upward again. Droplets and ice particles are caught in this maelstrom, growing, melting, refreezing, growing again, cycling through the cloud multiple times before finally escaping as precipitation. Some regions within the cloud are purely liquid water, droplets suspended in the warmer lower levels. Others are mixed with ice and what's called supercooled water, droplets that remain stubbornly liquid even at temperatures well below freezing, sometimes as cold as -20 or even -30 degrees Celsius. These supercooled droplets exist in a precarious state, ready to freeze instantly at the slightest disturbance. Supercooled water is one of nature's fascinating oddities. Pure water can remain liquid well below its normal freezing point if it's very pure and undisturbed, but it's in an unstable state. The slightest impurity, the smallest vibration, contact with any surface, and it freezes instantly. Aircraft flying through clouds containing supercooled water can accumulate ice rapidly on their wings and fuselage, a dangerous condition that has caused many accidents. When ice particles and supercooled droplets collide in the turbulent interior of the cloud, ice grows rapidly by collecting and freezing the liquid water droplets. It encounters a process scientists call accretion. As these growing ice particles bounce around violently in the chaotic updrafts and downdrafts, fragments break off constantly, creating smaller ice crystals that begin to grow in turn. The result is a turbulent cascade of collisions, freezing and melting, growing and breaking, a hidden storm within the visible storm. This is how hail forms. A small ice particle is carried upward by the updraft, collecting supercooled droplets as it rises, growing a layer of ice. It falls back down, perhaps melting partially, then gets caught in the updraft again and carried back up, growing another layer. This cycle can repeat multiple times. Each cycle adds another layer of ice. Cut open a large hailstone, and you'll see the layers, like tree rings, recording each trip through the storm. The largest hailstones require the strongest updrafts. A hailstone the size of a golf ball needs an updraft of at least 50 miles per hour to keep it aloft while it grows. A softball-sized hailstone, which occasionally falls in severe storms, requires updrafts exceeding 100 miles per hour. These are some of the most violent updrafts in nature. This is where lightning begins, its mysterious genesis, though not quite in the dramatic, simple way it's often imagined or depicted in movies. Inside the towering anvil of the mature cumulonimbus, countless collisions between ice particles of different sizes and types begin to separate electrical charges. Scientists believe the process works something like this. When small ice crystals collide with larger particles called graupel, which are essentially soft hail formed by supercooled water, freezing onto ice nuclei, charge is transferred between them. The exact mechanism of charge separation is still debated. Some scientists think it involves differences in surface temperature. Others point to the role of impurities in the ice. Still others focus on the mechanics of collision itself. But whatever the detailed mechanism, the result is clear. Small particles become positively charged while large particles become negatively charged. The lighter, smaller, positively charged ice crystals drift upward on the strong updrafts, carried like leaves in a hurricane, while the heavier, larger, negatively charged graupel and hailstones sink downward under their own weight despite the upward pull of the wind. This separation, this sorting, this gradual pulling apart of positive and negative charges builds an enormous electric field within the cloud, like tension gathering slowly in the air itself, like an invisible pressure building toward an inevitable release. The top of the cloud becomes predominantly positively charged, housing billions of positive ions in its icy crown. The bottom becomes predominantly negatively charged, a reservoir of electrons looking for somewhere to go, and the ground below, influenced by this massive negative charge hovering above it, develops a corresponding positive charge on its surface, especially on tall objects like trees, buildings, and towers that reach upward toward the cloud. The electric field strength builds gradually, from a few volts per meter in fair weather to hundreds of volts per meter under the cloud, to thousands, to tens of thousands. The air itself is being stressed. Molecules are being polarized. Electrons are being pulled one way, positive ions, the other. The air is being stretched like a rubber band, and like a rubber band, it can only stretch so far before it snaps. When the charge difference, the voltage difference, becomes too great to bear, when it finally exceeds the insulating ability of the air between them, the air itself breaks down, and a spark leaps through the sky. But this is no ordinary spark. This is lightning. Lightning is that spark amplified to a colossal, almost unimaginable scale. A lightning bolt begins with what's called a stepped leader, an invisible finger of ionized air that descends from the cloud in rapid, jerky steps, each step about 50 meters long, each one happening in about a microsecond. This stepped leader branches as it descends, creating multiple pathways through the air, searching for the path of least resistance to the ground. The stepped leader is invisible to the naked eye because it carries relatively little current and happens so quickly, but it's creating a conductive pathway through the normally insulating air, ionizing molecules, preparing the route for what's to come. It's like laying down a wire from the cloud to the ground, except the wire is made of ionized air. When one of these leaders gets close enough to the ground, within perhaps 50 or 100 meters, a streamer of positive charge reaches upward from the surface to meet it. This upward streamer typically launches from the highest point in the vicinity, a tree, a building, a tower, a person standing in an open field. The moment they connect, the instant the conducting pathway is complete, an enormous surge of current flows upward along the channel, about 30,000 amperes, 30,000 more current than flows through 1,000 homes. This return stroke, this massive flow of electricity, heats the narrow channel of air to temperatures exceeding 30,000 degrees Celsius, hotter than the surface of the sun, 5 times hotter than the sun's surface actually. In a channel perhaps an inch or 2 in diameter, temperatures reach levels normally found only in stellar interiors. The air expands faster than the speed of sound, creating a shock wave we hear as the sharp clap and rolling rumble we know as thunder. Thunder is literally the sound of air exploding. The superheated channel expands so rapidly that it creates a supersonic shock wave. That sharp crack you hear when lightning strikes nearby is the shock wave reaching your ears. The rolling rumble that follows is the sound arriving from more distant parts of the lightning channel and reflecting off clouds, hills, and buildings. You can estimate how far away lightning struck by counting the seconds between the flash and the thunder. Sound travels roughly 1 kilometer every 3 seconds or 1 mile every 5 seconds. So if you see the flash and count to 15 before hearing thunder, the lightning struck about 5 kilometers or 3 miles away. For something so violent, so powerful, that it can split trees and melt sand into glass, the process itself is fundamentally just simple physics multiplied by enormous scale. What begins as nothing more than a warm breeze drifting over a sunny meadow on a quiet afternoon becomes a tower, 15 kilometers high, carrying millions upon millions of tons of water and ice, releasing as much energy in minutes as a small nuclear power plant. A typical thunderstorm might release energy at a rate of 10 circumflex, 15 joules per hour. That's roughly the output of a large nuclear power plant. But instead of being harnessed and converted to electricity, all this energy goes into wind, rain, hail, lightning, and thunder. It's dissipated, scattered, returned to the environment. A thunderstorm is one of nature's most spectacular displays of energy release. It's powered entirely by rising air and phase changes, by water moving between its 3 states: evaporation from the warm surface below, condensation in the rising air, freezing in the upper reaches, and melting as rain falls back down, all happening simultaneously, all working in unison, recycling energy between invisible and visible states, between liquid, vapor, and solid. The power of a thunderstorm lies not in something alien or mysterious or supernatural, but in the same elegant water cycle that softens clouds at sunrise and paints rainbows after gentle showers. The same water molecule that evaporated from a tropical ocean last week might be part of a raindrop falling from a thunderstorm today. Next week it might be part of a snowflake. Next month part of a river. Next year part of another cloud. Even at its fiercest, at its most violent and intimidating, the cloud remains a masterpiece of balance and physics. The anvil top, spread wide across the sky like a blacksmith's anvil turned upside down, marks the precise point where upward momentum finally meets equilibrium, where the cloud can rise no further. The powerful updrafts, having spent their energy pushing water and ice to impossible heights, eventually give way to gentle descent as raindrops and ice begin their long fall back to Earth. The towering cumulonimbus is entering what meteorologists call its mature stage, the peak of its power and fury. Heavy with moisture accumulated over hours of growth, darkening ominously at its base, where precipitation hangs like a curtain. What once was a brilliant white puff of innocence now casts a deep foreboding shadow over the land below. The base of the cloud can appear almost greenish in severe thunderstorms, a color that many people associate with tornadoes. The green color probably comes from the way sunlight filters through enormous amounts of ice and water, mixed with the contrast against the dark cloud base. It has de notos nopals savum surfer here. It's an eerie, unsettling color that makes even experienced storm watchers nervous. Beneath it, standing on the ground looking up, the air feels different, charged, electric, and heavy with the scent of coming rain, ozone created by lightning and wet earth, and that peculiar metallic smell that comes before thunderstorms, all mingling together in the strange, expectant atmosphere. The wind might die completely, creating an eerie calm before the storm, or it might start gusting erratically, changing direction, picking up dust and debris. Birds go silent, animals seek shelter, The world seems to be holding its breath. When the first drops finally fall, when rain at last reaches the ground after its incredible journey, these drops have already lived an entire complex life inside the cloud. A single raindrop begins as a tiny cloud droplet that collided with thousands, perhaps tens of thousands, of others, growing larger with each collision and merger, growing heavy enough to overcome the upward pull of the wind. Each drop carries within it a memory of its journey, frozen, thawed, and refrozen countless times as it tumbled violently through powerful updrafts and downdrafts in the cloud's turbulent interior. A raindrop might have started as a microscopic cloud droplet at the base of the cloud. It rose in the updraft, collecting other droplets. It reached the freezing level and froze into an ice crystal. It continued upward, growing by collecting supercooled droplets. Eventually it became too heavy even for the updraft and began falling. As it descended, it melted back into liquid. It fell through the cloud base and finally reached the ground. The entire journey might have taken 30 minutes, or it might have taken several hours if it got caught in the updraft multiple times. By the time it reaches the ground and splashes on pavement or soil or your upturned face, it has traveled through more vertical motion, more up and down distance than most mountain climbers will experience in an entire lifetime of climbing. A drop that made several trips through a severe thunderstorm might have traveled 30 or 40 kilometers vertically. Even though it only fell 10 kilometers from cloud to ground, the rest was recycling through the storm. Eventually, inevitably, as the rain cools the air below the cloud, as that cooled air spreads outward along the ground, the updrafts begin to weaken and fail. The cloud's energy gradually runs out, its fuel supply of warm, moist air cut off by its own rain-cooled downdrafts. Its once mighty towers soften and lose their sharp definition, and the massive anvil begins to spread and thin, becoming more and more transparent. This is the dissipating stage, the death of the thunderstorm. The cloud has consumed all the available energy. The instability that fueled its growth has been eliminated. The atmosphere has been stabilized. The storm has done its job, moved heat upward, redistributed moisture, and now it can rest. The storm fades slowly into layered remnants that drift away on the upper winds, leaving behind only distant, diminishing rumbles of thunder and the sweet, clean smell of rain-washed air. That distinctive smell, called petrichor, comes from oils released by plants during dry periods, combined with a compound called geosmin, produced by soil bacteria. Rain releases these compounds into the air, creating that fresh, earthy scent we associate with storms. Within an hour or two, after the storm passes, after the darkness lifts and moves on, sunlight may break through the dispersing clouds again, and new small puffs of cumulus may already be forming in the warm, freshly moistened air left behind by the storm. Tiny seeds for the next generation of clouds, for the next cycle to begin. The storm has left its mark. Puddles on the ground, wet leaves dripping, soil saturated with moisture. The temperature dropped by several degrees, the humidity increased, and the atmosphere is temporarily more stable, less likely to produce another storm immediately. But give it a few hours, let the sun heat the ground again, let the moisture and warmth build once more, and the cycle might repeat. It's a remarkable, almost miraculous thought that every thunderstorm, no matter how enormous or powerful or frightening it may seem, no matter how much rain it drops or how much lightning it produces, begins with nothing more than a single bubble of warm air rising quietly from the sun-heated surface, from puff to power, from innocent playfulness to overwhelming grandeur. It's the same beautiful story told at vastly different scales. Each towering cumulonimbus, each thunderhead that makes us pause and stare in wonder or concern, is a living monument to sunlight and moisture working together. The Earth's elegant way of releasing stored heat back into the infinite coldness of space, and of reminding us, gently but unmistakably, that even the gentlest, most invisible forces Air, water, warmth can together build something truly spectacular, something powerful enough to shake the ground and light up the entire sky. The artists of the sky. Now let us slow down. Let us drift into a gentler space where clouds are not engines of violence but painters of beauty, where they work not with thunder and lightning but with light and shadow, where their canvas is the vast dome of sky and their medium is sunlight refracted through water and ice. Because clouds are artists, you see, patient, tireless artists who work every moment to create displays of colour and form that no human painter could ever match. They have been painting the sky since long before humans existed to appreciate their work, and they will continue painting long after we're gone. Consider the sunset, the daily miracle that has inspired countless poems, paintings, and songs throughout human history. What makes a sunset beautiful? What creates those brilliant reds and oranges and purples that stop us in our tracks and make us reach for our cameras? The answer, at its heart, is clouds. Clear skies at sunset are lovely, yes, but they're nothing compared to a sky scattered with clouds. The clouds become screens onto which light projects its final performance of the day. They catch the low-angle sunlight and reflect it back in 1,000 different hues depending on their altitude, their thickness, their composition. When the sun sits low on the horizon, when its light must travel through far more atmosphere than at noon, the shorter wavelengths of blue and green are scattered away by air molecules long before the light reaches your eyes. What remains is the longer wavelengths, the reds and oranges and yellows. This is Rayleigh scattering, named after the 19th century British physicist who explained it mathematically. But that alone isn't enough for a truly spectacular sunset. You need clouds. High cirrus clouds catch this reddened light and glow like embers. Mid-level altocumulus create waves of pink and orange. Low stratocumulus add depth and drama with their dark undersides, contrasting against the bright colours above. The most spectacular sunsets often follow storms. The atmosphere has been washed clean of dust and pollution. Humidity is high, and multiple layers of clouds at different altitudes create a three-dimensional light show. The highest clouds glow first, catching sunlight while lower clouds are still in shadow. Then, as the sun drops further, each layer lights up in turn, creating a cascade of changing colours that can last for an hour. And then there are the rare but unforgettable sunsets where the entire sky seems to catch fire, where clouds from horizon to horizon glow in impossible shades of red and purple, where the world briefly looks like it's been transported to an alien planet. These happen when volcanic eruptions inject fine particles into the stratosphere. The particles scatter light in unusual ways, creating colours and effects that can persist for months or even years after a major eruption. The eruption of Mount Pinatubo in 1991 created spectacular sunsets worldwide for more than 2 years. Artists painted them, photographers captured them, and millions of people simply stood and watched in wonder as the sky performed nightly shows, unlike anything in living memory. But sunsets aren't the only artwork clouds create. Consider the rainbow, that perfect arc of colour that appears when sunlight shines through rain. We all know what causes it. Broadly speaking, light refracting through water droplets. But the details are more intricate and beautiful than most people realize. When a ray of sunlight enters a raindrop, it slows down and bends, refracts, because water is denser than air. The different wavelengths of light bend by slightly different amounts. Red bends least, violet bends most. The light then reflects off the back of the droplet, a tiny mirror curved into a perfect sphere, and exits the front again, refracting once more as it leaves. The result is that white sunlight splits into its component colours, and because of the geometry of spheres and the specific refractive index of water, the colours emerge at specific angles. Red light emerges at about 42 degrees from the direction of the incoming sunlight. violet at about 40 degrees. So when you see a rainbow, you're seeing light from countless raindrops, each one contributing just one color to your eye based on its position in the sky. The drop that contributes red to the rainbow is slightly higher than the one contributing violet, and both are at precisely the right angle from the anti-solar point, the point directly opposite the sun from your perspective. This is why rainbows always appear as perfect arcs centered on the anti-solar point. It's why they're always opposite the sun. It's why you can never walk to the end of a rainbow, because the rainbow moves with you, maintaining that constant angle. And sometimes, on lucky occasions when conditions are perfect, you might see a double rainbow. The fainter secondary bow appears above the primary, with colors reversed, and the sky between the two bows noticeably darker than the sky outside them. This darker region is called Alexander's dark band, named after Alexander of Aphrodisias, who first described it around 200 AD. The secondary rainbow forms from light that reflects twice inside the raindrop before exiting. Each reflection reverses the order of colors, and because more light is lost with two reflections rather than one, the secondary bow is always much fainter than the primary. Very rarely, perhaps once or twice in a lifetime, if you're lucky and observant, you might glimpse supernumerary bows. These are faint-colored bands visible just inside the primary rainbow. They appear green and purple, and they result from interference of light waves, from quantum mechanical effects that classical physics can't fully explain. They're a reminder that even something as familiar as a rainbow contains mysteries and complexities that still inspire research and wonder. Clouds create other optical phenomena too. The glory, a series of colored rings that appear around the shadow of your airplane when flying through or above clouds. It's caused by light being scattered backwards by cloud droplets, and it's related to the rainbow but with a different geometry. From an airplane window, you might see the glory surrounding the shadow of the plane, like a colored halo marking your passage through the sky. Halos around the sun or moon, created when light passes through the hexagonal ice crystals in cirrus or cirrostratus clouds. The 22-degree halo is most common, but there are dozens of possible halo phenomena, arcs and circles and spots of light, each caused by light taking a specific path through specific crystal orientations. Serious halo watchers keep logs of what they've seen, checking off rare phenomena like the circumzenithal arc, a brilliant upside-down rainbow straight overhead, or pari-arcs that appear as extensions of the 22-degree halo. Sundogs, those bright spots on either side of the sun, are particularly common in cold climates where ice crystals are abundant. They're caused by light passing horizontally through plate-shaped ice crystals that are falling with their flat faces horizontal. The crystals act like prisms, bending the light and spreading it into colors. There are light pillars, vertical shafts of light extending above or below the sun or moon, created when light reflects off ice crystals falling with their faces horizontal. On cold winter nights, you might see light pillars above street lamps or stadium lights, the artificial light creating the same effect as the sun. And there's the green flash, that legendary phenomenon where the sun appears to flash green for just a second or two as it sets or rises. It's real, despite its reputation as a sailor's tall tale. It requires a very clear horizon, and happens when atmospheric refraction separates the colors of sunlight, and the last sliver of sun to disappear is the green wavelength. Clouds also create beauty through shape and form alone. The lenticular clouds that form over mountains, smooth, lens-shaped discs that hover in place even as strong winds blow past them. They mark standing waves in the airflow, oscillations that remain stationary relative to the ground even as air rushes through them at high speed. From a distance, they look so artificial, so precisely shaped, that they're often mistaken for UFOs. Mammatus clouds, those strange bulging pouches that hang down from the bottom of cumulonimbus anvils. They form when pockets of air in the anvil become negatively buoyant and sink, creating these distinctive bubble-like formations. They often appear after the worst of a storm has passed, catching the evening light in their curved surfaces, creating an alien landscape overhead. Roll clouds, long, horizontal tubes of cloud that appear low in the sky and seem to rotate slowly around their horizontal axis. They form along outflow boundaries from thunderstorms or along sea breeze fronts, marking the leading edge of cooler air advancing like a wave through warmer air. Watching one approach is mesmerizing. A cloud cylinder, stretching from horizon to horizon, advancing silently, except for the wind that precedes it. Noctilucent clouds, the highest clouds in Earth's atmosphere, forming around 80 kilometers altitude in the mesosphere. They're visible only in summer at high latitudes, and only during twilight when the sun has set at ground level, but still illuminates these ultra-high clouds from below the horizon. They glow with an eerie electric blue light and appear as silvery waves and tendrils against the darkening sky. They're composed of ice crystals forming on microscopic dust particles, possibly including meteor dust, at temperatures approaching -130 degrees Celsius. They're so high that they exist in what's essentially the edge of space. And then there are the purely artificial cloud phenomena, contrails left by aircraft at high altitude. These are human-made cirrus clouds, ice crystals forming in the wake of jet engines. Sometimes they dissipate within minutes. Other times, if the atmosphere is humid and stable, they can persist and spread, eventually becoming indistinguishable from natural cirrus. On busy flight routes, the sky can become crossed with contrails like a tic-tac-toe board, slowly spreading and merging until they form an artificial overcast layer. Clouds inspire wonder, not just through grand displays but through small, intimate moments. The way a single cumulus cloud can perfectly frame the moon, the way fog clings to valleys in the morning, filling them with a sea of white while hilltops poke through like islands, the way steam rises from your coffee cup in swirls and eddies, a miniature demonstration of fluid dynamics. They've inspired artists for thousands of years. Chinese landscape paintings often feature clouds as important compositional elements, not just background, but subjects in their own right. European masters of the Renaissance studied clouds carefully, understanding that realistic clouds would make their paintings more convincing. The Romantic painters of the 19th century made clouds central to their work, using them to create mood and emotion. John Constable, the English landscape painter, was obsessed with clouds. He made hundreds of cloud studies, small oil paintings done quickly outdoors to capture specific cloud formations and lighting conditions. He wrote detailed notes on the backs of these studies, recording the date, time, wind direction, and weather conditions. He understood that clouds weren't just pretty decorations, but specific, measurable phenomena that followed rules and patterns. Photographers have similar obsessions. There are photographers who specialize in storm clouds, chasing severe thunderstorms across the Great Plains to capture their power and beauty. Others focus on clouds at dawn and dusk when the light is most dramatic. Still others use time-lapse photography to show how clouds build and dissolve, revealing dynamics invisible to the naked eye. And then there are the cloud watchers, ordinary people who simply enjoy looking up. The Cloud Appreciation Society, founded in 2005, has hundreds of thousands of members worldwide. They share cloud photos. They learn to identify cloud types. They appreciate clouds not as harbingers of bad weather, but as beautiful, fascinating phenomena worthy of attention in their own right. Perhaps we should all be cloud watchers. In our busy lives, we often forget to look up. We move from building to car to building, our eyes on our phones or straight ahead. But overhead, often unnoticed, the sky is putting on a show. Clouds are forming and dissolving. Colors are changing. Light is painting temporary masterpieces that will never be repeated exactly the same way. The next time you're outside, take a moment to look up. Really look. Notice what type of clouds are present. Watch how they move. See if you can spot a rainbow, or a sundog, or just an interesting shape. Let yourself be present with the sky for a few moments. Because clouds are gifts, really. Free entertainment provided by physics and thermodynamics. Free art, painted by nature on the grandest canvas imaginable. And all we have to do to enjoy them is look up and pay attention. And so we come to the end of our gentle journey through the secret life of clouds, from their invisible beginnings as water vapor, through their birth at the dew point, their organization into families and types, their growth from innocent puffs to powerful thunderheads, and their artistry painting the sky with light and color. We've learned that clouds are both simple and complex. Simple in their basic ingredients, just air and water. Complex in their behavior and their effects on our planet. We've seen that they follow physical laws yet remain unpredictable in detail, that they can be understood by science yet still inspire poetry and wonder. But perhaps most importantly, we've been reminded to notice them, to look up, to appreciate these floating islands of vapor that are working every moment to keep our world balanced and beautiful. The clouds above you right now, wherever you are part of this ancient cycle. They're connected to clouds thousands of miles away. They're connected to the ocean that evaporated the water that formed them. They're connected to the next storm that will bring rain to someone's garden somewhere. Everything is connected through water and air and energy, and clouds are the visible manifestation of those connections. They're the atmosphere showing its work. The water cycle made visible, physics transformed into art. So, the next time you see a cloud, don't just glance and move on. Pause, look, wonder. Ask yourself what type it is, where it came from, where it's going, what weather it might bring. And know that you're looking at something truly remarkable, something that poets and scientists both find endlessly fascinating, something that has shaped our world and will continue shaping it long after we're gone. The clouds will keep drifting, keep forming and dissolving, keep painting the sky, keep bringing rain and snow, keep regulating our climate, keep doing the work they've done for billions of years. And we get to watch, to appreciate, to marvel. What a gift that is. Sleep well, dear listener, and may your dreams be as soft and gentle as fair weather cumulus on a summer afternoon. May they drift peacefully across the landscape of your mind, and may you wake tomorrow with a renewed appreciation for the simple wonder of water suspended in air, painting beauty across an endless sky. Good night. The ocean's blanket. Far out over the ocean, far, far from the sight of any land, where the horizon curves gently away in all directions like the edge of a great blue sphere, where nothing interrupts your view for hundreds or even thousands of kilometers, lies one of Earth's most important and yet most quietly appreciated wonders. A vast glowing quilt of cloud that stretches endlessly to every horizon you can see. These are the marine stratocumulus clouds, the silent, steadfast guardians of the planet's temperature, the unsung heroes of our climate system. From above, from the perspective of a satellite orbiting hundreds of kilometers overhead, looking down at the Earth below, they appear as endless plates of brilliant white stitched together in soft, rolling patterns, like a patchwork quilt made by patient hands over centuries. From below, from the deck of a ship moving slowly through the gentle waves, they turn the sky into a pale, uniform ceiling, shading the waters beneath, with their gentle, persistent, unchanging presence. Together, these vast cloud decks act as nature's biggest duvet, nature's most expansive blanket. Do not attempt to fold, and definitely don't try to wash in a machine. Despite their calm, almost monotonous appearance, despite how ordinary and unremarkable they might seem to a casual observer, these clouds play a commanding, absolutely crucial role in the global climate. They cover about 1/5 of the entire Earth's surface at any given moment, roughly 20% of our planet. That's an area larger than all of Asia. They form particularly above the cool waters of the eastern oceans, those specific regions where conditions are just right. The Pacific Ocean off the western coast of South America, along Peru and Chile, the Atlantic Ocean off the western shores of Africa, along Namibia and Angola, and the waters near California, stretching from San Francisco down toward Baja. These special regions are known to oceanographers as cold tongue zones, where powerful upwelling ocean currents bring cold water from the depths far below to the surface. Deep water, water that hasn't seen sunlight in years or decades or even centuries, rich in nutrients, but bitterly cold, rises to replace warmer surface water. As warm, moist tropical air from the equator drifts over these chilled seas, as it encounters this unexpected pool of coldness, it cools from below, forming thick layers of stable air capped by what meteorologists call a strong temperature inversion. Within this shallow layer of atmosphere, perhaps only a kilometer or two deep, maybe just a few thousand feet thick, a delicate, precise balance is struck between upward mixing driven by the ocean's slight warmth and the cooling influence of the sea beneath. And that balance, that perfect tension between warmth trying to rise and coolness holding it down, gives birth to the extensive marine stratocumulus deck. The temperature inversion is the absolute key to understanding these remarkable clouds. Normally, as we've learned earlier in our journey tonight, air temperature cools as you rise through the atmosphere. That's the standard pattern, the expected behavior. But in these special regions over cold ocean waters, something different happens, something unusual. A warmer layer of air heated by the sun or blown in from warmer regions, sits on top of the cooler air near the surface. Temperature actually increases with height, instead of decreasing. This creates what acts like an invisible lid, an atmospheric ceiling, trapping moisture and turbulence in the layer below. Clouds forming beneath this inversion can't rise freely through this lid. They can't punch upward into towering cumulus, the way they might over warm land. The stable, warmer air above simply won't allow it. So instead, with nowhere to grow vertically, they spread out sideways, horizontally, forming vast, thin sheets that can stretch for thousands upon thousands of kilometers, covering areas the size of countries, sometimes the size of continents. It's the atmosphere's way of saying firmly but gently, you may grow, yes, but only in two dimensions, width and length, but not height. The result is a cloud field so remarkably uniform and persistent that it shows up clearly in satellite images as bright, glowing patches against the darker blue of the sea below. These clouds can persist for days, even weeks at a time, covering the same region with remarkable consistency day after day, rarely changing, rarely moving much, just sitting there patiently over the cold waters. Inside these seemingly still, unchanging layers, beneath that uniform appearance, the air is anything but motionless. Small pockets of slightly warmer air rise slowly, gently from the ocean surface below, heated just enough by the water to become buoyant, while cooler air chilled by evaporation and radiation, sinks back down toward the sea, creating a slow rolling convection, gentle overturning cells, each one only a few hundred meters tall, each one completing its cycle over minutes or hours. The tops of these convective cells form the visible cloud layer you see from a satellite or ship. Their bottoms touch or nearly touch the ocean surface below. This quiet, persistent churning helps to mix moisture and heat continuously through the shallow layer, keeping the cloud alive hour after hour, day after day, week after week. Occasionally, small drops of drizzle form within the cloud deck and begin their slow fall toward the ocean. But these drops are usually tiny, barely more than large cloud droplets, and they rarely reach the surface intact. Instead, they fall a few hundred meters before evaporating in the slightly drier air below the cloud base. Just enough evaporation to maintain the delicate balance between condensation happening above and evaporation happening below. From a climate perspective, from the viewpoint of Earth's energy balance, these unassuming, ordinary-looking clouds are absolutely crucial. They reflect an enormous amount of incoming sunlight back into the infinite darkness of space, keeping the ocean beneath them cool. Their bright white tops act like mirrors, bouncing solar radiation away before it can warm the water. Without this reflective blanket, without these persistent clouds, the tropical oceans would absorb far more solar energy, warming dramatically, which would warm the entire planet significantly. The feedback would be substantial and concerning. Scientists studying climate estimate that marine stratocumulus clouds have a net cooling effect on Earth's climate that actually rivals, the warming effect of all human-produced greenhouse gases combined. They are, quite literally, and without exaggeration, one of the planet's most important thermostats, one of the most powerful cooling mechanisms Earth possesses. Yet despite their importance, they remain fragile, vulnerable to change. As the planet warms due to increasing greenhouse gases, the delicate balance that creates these clouds may shift in concerning ways. If the ocean's surface warms too much, if it exceeds certain critical thresholds, or if the temperature inversion weakens and breaks down, these vast cloud decks could thin dramatically or even break apart completely. Revealing dark ocean water beneath that would absorb even more heat from the sun, leading to more warming, which could cause more clouds to disappear, which would cause even more warming. It's a potential positive feedback loop that climate scientists watch carefully with increasing concern, a tipping point written in vapor and light, a critical threshold we may be approaching. Standing on the deck of a ship beneath one of these extensive cloud decks, sailing for hours or days under their persistent cover, you might find the view somewhat monotonous after a while. The same unchanging grey-white ceiling stretching endlessly in every direction you look. No variation, no drama, no towering thunderheads or delicate cirrus, just uniform greyness. The light filtering down is soft and diffuse, lacking the drama and majesty of towering thunderheads, or the delicate beauty of high cirrus catching the sunset. It's neither bright nor dark, just a constant even greyness that seems to go on forever. But there's a quiet, understated beauty in this monotony, if you know how to see it. A reminder that not all of nature's wonders need to be dramatic or spectacular to be important, to be essential. Sometimes, perhaps more often than we realize, the most essential things are the ones we barely notice, the ones working quietly in the background. The steady, patient breath of the ocean, the persistent cooling of the planet, the soft blanket of clouds that keeps our world from overheating. These things happen without fanfare, without announcement, without demanding our attention. These clouds teach us an important lesson, if we're willing to listen. They teach us that power doesn't always announce itself with thunder and lightning. That importance doesn't require drama. Sometimes the most powerful forces work in whispers, covering a quarter of the world's oceans with a simple message written in white. I am here, they say quietly, persistently, and I am keeping watch over the planet. I am keeping things cool. I am maintaining balance. The fading light. Every cloud, no matter how grand or persistent, no matter how powerful or enduring it may seem, must eventually fade. It's one of the fundamental truths of the atmosphere. The same delicate processes that birth them, that lift them skyward and fill them with moisture, will one day reverse, and the cloud will dissolve gradually back into invisible vapor. This dissolution, this return to invisibility, is as beautiful and poetic as the formation itself. Though we rarely stop to watch it happen, we notice clouds appearing, but we seldom pay attention as they fade away. As evening approaches and the sun sinks lower and lower toward the western horizon, painting the sky in shades of orange and pink, the ground begins to cool. The warmth that drove thermals upward during the bright afternoon gradually fades away with the failing light. The Earth stops radiating heat upward. The engine that powered the day's convection shuts down. Without that constant, reliable supply of rising, moisture-laden air, without fresh parcels of warm air, continuously feeding them from below, the clouds begin to lose their source of sustenance. Like a fire running out of fuel, they start to weaken. The edges fray first, becoming softer, more transparent, more wispy. Dry air from the surroundings, air with lower relative humidity, mixes in through that process we discussed earlier called entrainment. This drier air evaporates droplets at the cloud's boundaries, eating away at the edges like invisible erosion. What was once a crisp, well-defined puff with sharp boundaries becomes wispy, ethereal, ghost-like, like a memory starting to blur around the edges, like a dream fading as you wake. From below, standing on the ground looking up, you can watch this entire process unfold in slow motion if you're patient enough. A cumulus cloud that seemed so solid and permanent just an hour ago, so substantial and real, begins to thin visibly. Patches of blue sky appear through its body like windows opening. The base rises higher as the lowest droplets evaporate first. The top softens and loses its billowing, sculptural quality, no longer sharp against the sky. Within minutes, sometimes within just 10 or 15 minutes, what was once a substantial, impressive cloud becomes little more than a faint smudge against the blue, and then, gradually, nothing at all, gone completely, vanished. But the water hasn't disappeared, of course. Water doesn't just cease to exist. It has simply returned to its invisible form, back to vapor. The molecules are still there, still floating in the air, still present but unseen, patiently waiting for the next cycle to begin, for the next opportunity to condense and become visible once more. This daily rhythm, this breathing of the sky, happens so reliably, so predictably, that we often take it completely for granted. We don't even think about it. Morning brings clear skies as the cool night air, having lost its warmth to space, can hold little moisture without condensing it into fog or dew. As the sun climbs higher through the morning, as it warms the land with increasing intensity, clouds begin to form. Small at first, then growing through the late morning and afternoon, until they reach their peak around mid-afternoon, around 2 or 3 p.m., when the sun's heating is strongest. Then, as evening approaches and shadows lengthen, they fade away once more into the darkening sky. It's the pulse of the atmosphere, as regular and reliable as breathing, as natural and inevitable as the tide flowing in and out. Inhale, exhale, form, dissolve, visible, invisible. Some clouds, of course, last longer than a single day. Large storm systems associated with weather fronts can maintain their clouds for days at a time, as the fronts move slowly across continents and oceans. Marine stratocumulus decks, as we just learned, persist for weeks over cold ocean waters, fed continuously by the moisture evaporating from the sea below. High cirrus clouds, made entirely of ice crystals, instead of liquid water, can drift for hundreds of kilometers, sometimes over 1,000 kilometers, before finally sublimating, turning directly from ice back to vapor, without ever becoming liquid, disappearing slowly as the crystals evaporate one molecule at a time. But even these persistent, long-lasting clouds are temporary in the grand scheme of things. Everything in the atmosphere is in constant flux, constantly exchanging energy and matter between forms, never truly still, never permanent. The atmosphere abhors permanence. There's something deeply comforting about this impermanence when you really think about it. Something peaceful and reassuring. Clouds remind us gently that change is not only inevitable, it's beautiful. They teach us that transformation is natural, that what appears solid can become invisible in moments, that what seems gone, what appears to have vanished, will return in a new form when conditions are right. As you lie there tonight, perhaps feeling your own thoughts beginning to slow like a river reaching calmer water, your own awareness starting to drift like a cloud on a gentle wind. You might think of yourself as being a bit like a cloud, similar in some fundamental ways, made of countless small parts working together in harmony, constantly changing shape from moment to moment, sometimes clearly defined with sharp boundaries, other times hazy and uncertain, boundaries blurred, formed by invisible forces you can't always see or understand, sustained by energy and processes you can't always identify. And just like a cloud, you too follow cycles, waking and sleeping, day and night, active and resting, moving and still, visible to the world and withdrawn into yourself. Each day you reform, you gather energy from food and rest and sunlight, and then you release it as night falls, letting it go, allowing yourself to dissolve into sleep. Each breath you take right now is part of the same atmosphere that makes clouds possible, the same oxygen and nitrogen molecules, the same water vapor that will one day become part of a cloud, or perhaps already has been, countless times throughout Earth's history. You are, in a very real sense, part of the sky's breathing, connected intimately to every cloud, every breeze, every drop of rain that has ever fallen. You're not separate from the atmosphere, you're part of it. Every breath in, every breath out. You exchange molecules with the air around you. Molecules that were once in clouds, molecules that will be again. And so, as we near the end of this gentle journey through the secret life of clouds, as our time together tonight draws to a peaceful close, let's take a moment to simply rest with what we've discovered, to let it settle, to let it sink in. We've learned that clouds are born from the simplest ingredients imaginable: air, moisture, and tiny specks of dust or salt smaller than you can see. We've seen how they grow from invisible vapor into towering monuments that reach the edge of space, how they're classified into families with elegant Latin names that have endured for centuries, and how even the mightiest, most powerful thunderstorm, with all its sound and fury, begins as nothing more than a single puff of white floating above a sun-warmed field. We've floated above vast ocean blankets that cool the planet, that maintain the delicate balance of Earth's temperature, and we've watched as clouds fade back into invisibility, when their brief time is done, returning to vapor, waiting to form again. But more than facts and physics, more than temperatures and altitudes and Latin names, perhaps what clouds teach us most is patience. They remind us that beauty doesn't need to be permanent to matter deeply, that complexity and grandeur can arise from simplicity, that the sky above us, though it appears empty and featureless at times, is actually teeming with life and motion and constant transformation every moment of every day. Every cloud you see is a small miracle when you really stop to consider it. A collaboration between ocean and air, between sunlight and shadow, between the solid earth below and the infinite space above. A temporary sculpture made of nothing but water and air, yet substantial enough to shade entire cities, to water vast forests, to paint the sky in endless patterns. So the next time you find yourself gazing upward, whether it's at a perfect summer cumulus drifting lazily by, or a grey blanket of stratus on a rainy day, or towering thunderheads on the horizon, remember what you've learned here tonight. Remember that each cloud has its own story, a beginning in rising air and condensing vapor, a life of constant change and motion and transformation, and an ending in the soft, inevitable return to invisibility. But not really an ending, just a transition, a change of state, a continuation of the eternal cycle. And as your own thoughts continue to slow now, as your breathing deepens and becomes more regular, as you feel yourself drifting like a cloud on a gentle wind towards sleep, know that you've spent this time well, learning, wondering, exploring, and allowing yourself to be carried by curiosity into the peaceful realm of rest. The clouds above are still moving in their ancient, timeless patterns right now. The atmosphere is still breathing, in and out, day and night. And you, dear viewer, dear friend, are part of that same beautiful, endless cycle, part of the earth breathing, part of the water cycle, part of everything. Thank you truly for joining me on this quiet journey tonight. I hope it brings you peace, deep rest, and perhaps the sweetest, most restful dreams. Until next time, until we meet again, sleep well. The sky will still be there in the morning when you wake, with new clouds to watch, and new stories written in vapor to read, and new wonders to discover. Good night.